Hello to the Skin Image Analysis Workshop at CVPR. My name's Matt Groh, and I'm a graduate student at the MIT Media Lab. I work on conceptualizing and evaluating data-driven socio-technical systems. I'd like to share with you recent research evaluating classification of skin disease in images. Now, this work is a product of a fairly large collaboration, including Caleb Harris and Louise Swankson, who are both also from MIT, Felix Lau, Rachel Hahn, and Aaron Kim, who are from Scale AI, and Arash Kuchek and Omar Bedri, who are both board-certified dermatologists in the US. So to get us started, I'd like to share some headlines from this past year. Now, dermatology has a problem with skin color. Specifically, the visual appearance of skin conditions can be quite different on light and dark skin. Yet, most dermatologists in the US are trained on mostly lighter skin. Darker skin is underrepresented in dermatology residency programs, textbooks, research, and diagnoses, unfortunately. And in this talk, I'll discuss what's at stake for the future of skin image analysis. Our main research question is, how does the accuracy of deep neural network models trained to classify clinical images as skin conditions vary across skin color? As an initial step to address this question, we developed the Fitzpatrick 17K dataset, which is a collection of nearly 17,000 clinical images of skin conditions that we annotated with skin type labels. The dataset is now publicly available, and we trained a deep neural network to classify skin conditions, and I'll share how skin type affects accuracy scores. In addition, I'll discuss Fitzpatrick's skin type labels and how they compare to an individual typology angle. We'll conclude with a discussion of these results and their implications for future research. Now, with only one exception, none of the publicly available datasets identified by this workshop include skin type labels. The exception is the PAD UFIS 20, which is a skin lesion dataset composed of patient data and clinical images collected from smartphones. This is a good start. And there's a huge opportunity to improve these datasets by simply annotating the images with skin type. The reason it's important to annotate clinical dermatology images with skin type is that without these annotations, hidden biases can lurk in the data. So in 2018, Joy Bulamwini, my colleague at the MIT Media Lab, and her co-author Timnit Gebru published their Gender Shades paper, which revealed that commercially available facial recognition systems were substantially more accurate on lighter-skinned individuals than darker-skinned individuals. So if there are accuracy disparities across skin type and facial recognition, and we know that skin conditions look different across skin types, then we have good reason to think that there might be accuracy disparities in automated skin image analysis when we start to consider the diversity of skin types from color to thickness to amount of hair and so on. So when it comes to machine learning in healthcare, it's an ethical imperative to rigorously examine potentials for discrimination across the entire machine learning model development pipeline. In this talk, I'll highlight the issues with the data collection process, examine how deploying a model on an underrepresented group can potentially create harm, and consider the subjectivity and ambiguities involved in trying to measure skin type. Now, the images and their corresponding labels in this Fitzpatrick 17K dataset are sourced from two online open source dermatology atlases, DermaAmine and Atlas Dermatologico. These images have been cited in the dermatology and computer vision literature a number of times, and we're not the first to analyze these images. But I want to be very clear that these images are not perfectly labeled. First, we do not know if these labels have been confirmed by a biopsy. And second, we have two board-certified dermatologists in the US who took a look at a random sample of over 3% of the data, about 500 images. And we note in the paper that 69% of the images are labeled as diagnostic of the labeled condition, and another portion of the images are potentially diagnostic, but not clearly diagnostic, and further testing is needed to confirm the diagnosis. And then 3.4% of the data are considered wrongly labeled. This error rate is consistent with the error rate in the most commonly used datasets for computer vision, NLP, and audio processing, and it's something to address in future research. Now, the skin condition labels reflect three types of categorization, which are based on the skin lesion taxonomy developed in the 2017 paper published in Nature by Andrea Stiva and colleagues. At the most basic level, skin conditions are labeled as non-neoplastic, malignant, and benign, and the next level breaks this down into 9 categories. At the most granular level, our dataset has 114 conditions, and each condition has a minimum of 53 images. We include the most common skin conditions in these 2 atlases and exclude a number of categories that were considered too broad of categories or had images of low quality. Now, the images are annotated with Fitzpatrick skin type labels by a team of human annotators from Scale AI. The Fitzpatrick labeling system is based on a 6-point scale originally developed for classifying sun reactivity of skin and adjusting clinical medicine according to skin phenotype. Each image was annotated by 2 to 5 annotators based on Scale AI's dynamic consensus process. The number of annotators per image is determined by a minimal threshold for agreement, which takes into account an annotator's historical accuracy evaluated against a gold standard dataset, which was annotated by board-certified dermatologists. And I'll note here that Fitzpatrick skin types are subjective, and particularly so when they are based on images with different lighting conditions and levels of detail. We find that annotators annotate images within plus or minus 1 of the board-certified dermatologist's annotation in about 80% of trials. In a moment, we'll discuss how apparent Fitzpatrick labels compare to other methods for measuring skin tone, but the important thing to take away here is that annotators do a generally good job at matching the board-certified dermatologist's labels. Now, the Fitzpatrick 17K dataset is imbalanced, and there are many times more images of light skin than dark skin. Moreover, the distribution of conditions is imbalanced. The dataset has at least 1 image of all 114 skin conditions for the 3 lightest skin types, but it's missing a couple skin types in Fitzpatrick type 4 and 5. And it's missing 25 of the 114 skin conditions. That's over 20% of skin conditions in the Fitzpatrick skin type 6. This dataset is far from perfect and highlights the need to collect more data. Now, here's the PyTorch code on the left for training a VGG16 deep neural network architecture. We adapted the architecture and placed the last fully connected 1,000-unit layer with the following sequence of layers: a fully connected 256-unit layer, a ReLU layer, a dropout layer with 40% chance of dropping, and a layer with a number with 114 categories, and then finally a softmax layer. We also include a number of transformations to improve the performance of the model, including random resizing, random rotation, random altering of brightness, contrast, saturation, hue, random horizontal flipping, center cropping, and normalizing the image arrays to image net means and standard deviations. Now, we evaluate the model on 7 training test splits. The verified holdout set refers to the subset of images that our board-certified dermatologists identified as diagnostic of the labeled condition. The random holdout set is selected at random while stratifying on skin conditions, and the next 2 holdout sets are based on the image source. And the last 3 holdout sets are based on Fitzpatrick annotations. Now remember, this task is to classify an image as one of 114 skin conditions. So we see that we're getting 27% accuracy on the verified dataset, and 27% when we train on DermaAmine and test on Atlas Dermatologico data. When we examine high-level categorization accuracy in the random holdout, we find that our results approach the accuracy levels of the 2017 Nature paper from which we obtained these high-level categories. Now, when we look at the first 4 train test splits, we don't find really a systematic relationship between accuracy and skin type. But in the last 3 train test splits, we can start to answer our question. If we train our neural network model on skin conditions in light skin, how well will it do on dark skin, and vice versa? What we find is the model is most accurate on skin types closest to the skin types in the training data. This means that model accuracy depends on representation of skin conditions across skin types, and the underrepresentation of dark skin types in the dataset and other datasets is concerning. It's imperative to address this underrepresentation to improve accuracy in skin image analysis. Now, I'll mention that Fitzpatrick skin type classification is one of many ways to classify skin types and has both advantages and disadvantages. As researchers interested in skin image analysis, we're interested in how well automated methods might correspond to Fitzpatrick skin types in clinical images, because it's much cheaper to run an algorithm to classify skin types than to hire people. But the question is it just as accurate? So we calculate ITA scores for all images in the Fitzpatrick 17K dataset and compare them to the Fitzpatrick skin type labels. Here are the distributions for ITA calculated over the full image and ITA calculated over a YC-BCR mask, which is intended to exclude non-skin pixels. We see a general correspondence. The means go down and to the left. But we see that ITA produces quite a large range of values for each Fitzpatrick skin type. This next plot, shows you ITA values on the y-axis and Fitzpatrick skin labels on the x-axis for a sample of 18 images. From a visual inspection, the discrepancy between ITA values and Fitzpatrick labels seems to be mostly driven by variance in ITA values, like this image of a foot. So, in summary, I'd like to highlight that dark skin is underrepresented, and this has consequences for how accurate skin image analysis is, because skin conditions look different across skin types. We find that current automated methods for calculating skin type are noisy and may be an avenue for future research. An open question that I'd like to consider is how well do dermatologists classify skin conditions across skin types, and how might we build decision support systems to help dermatologists more accurately diagnose skin conditions? We hope this research inspires consideration of skin type and additional heterogeneity in skin image analysis. Thank you for your time.